So in this lecture session, I am going to discuss under statistical process control some of the important issues like the fundamentals of control chart construction, the principles of rational subgrouping, selection of the sample size and number of samples, rules for identifying out of control process, plus I also want to introduce the concept of control charting for the attributes data. Okay, so these are all very vital issues as far as construction of a control chart is concerned, and many a time you go for interpretation of the control chart, and there must be right kind of interpretation from a control chart, and so that say we actually know that what extent the process has been maintaining a state of statistical control, and it all depends on whether you have constructed a control chart following the specific rules, guidelines and principles. Now but the entire control chart that depends on how would you select the sample and from the population, from the process, and there are many other factors. So as far as getting a sample is concerned from the population or from the process, there are certain principles you have to follow, and these are referred to as the principles of rational subgrouping. Subgrouping means essentially the sampling, and the Shewhart, who is referred to as the father of statistical process control, who introduced the concept of control charting for initially for the manufacturing processes. He mentions the fundamental criteria for the selection of rational subgroups. That means what are the basic criteria based on which you should select a sample or you should create a sample. The premise is a rational sample is chosen in such a way from the process that the variation within the sample is considered to be due to only common causes. That means what you expect that within the sample the variation should be as minimum as possible, and the samples are selected such that if special causes are present, they will occur between the samples. That means what we try to do, that means so we take a sample from at a particular point in time, or at instant of time, or during period of time, and while you take a sample, while you form the sample from the population, now so you need to take the measurements from the samples. Now condition should be such that these the measurements data which you get from a sample, okay, now when you analyze this data, you will find there are the minimum differences between this data. So that condition you have to ensure. Whereas one sample is not sufficient, so you must have multiple samples over the time periods. So why do you have multiple samples? That means make sure that the differences between the samples should be as maximum as possible. So there are two the principles we follow while you form the sample, while you select the number of samples from a process. The differences between the samples should be maximized, and the differences within the samples should be minimized. Okay, so these are the two vital principles, and these principles are referred to as principles of rational subgrouping. Now First, you select the sample, and then you consider the frequency of sampling, which is nothing but the determination of the number of samples for construction of a control chart. Fine. So first you construct the control chart, and then you start using it, and after its use, you check whether it is performing well or not. That means whether the control chart is performing as per the objectives for which the control chart is in use. So for that, the two specific the performance measures we always use. One is the operating characteristic curve, or the OC curve, or the control chart, and the second one is the ARL curve. Okay, so these the two performance measures I have already discussed. Now the selecting sample size, that is essentially the number of units in each sample that is to be determined, is a necessity in using a control chart. So that is very, very clear. Otherwise, you just cannot construct the control chart. If we can tolerate smaller changes in the process parameters, this point is to be noted. A small sample size might be sufficient. Is it okay? There are process settings like with respect to a machining process, it could be like say the spindle speed, or the feed rate, or say the depth of cut with respect to a specific operation, say turning, and there are many other process parameters depending on the types of say the processes that we deal with. Alternatively, if it is important to detect slight changes in the process parameters, that is very, very important. Like there are many sophisticated processes you deal with. Okay, certain, even if there is a minimum change in the process parameter settings, it has to be detected. So in that case, you need to have a large sample size. Sampling frequency, that means the number of samples to be considered for constructing a control chart, must be decided prior to construction of the control charts. This point I have already emphasized. Choosing large samples very frequently is the sampling scheme that may provide maximum information. That means it should be as many as possible. But just keep in mind at this stage, but there is, as such, there is no formula, or say some sort of the formula which you may use for determining say the number of samples. So it based on what kind of processes you are dealing with. You must have an idea about the amount of variability in the process, and accordingly you decide. Now, as I have been telling you all the time, that the main purpose of constructing a control chart, main purpose of using a control chart is to identify out of control process. That means what we will assume that once you start the process, our null hypothesis is that the process is in control. Otherwise, how do you start the process? Okay. So now what you need to do in a running process, okay, you need to be on your toes. You must check whether something has gone wrong and the process has gone out of control or not. So for that, this particular tool called control chart is used. Now, the researchers, they have proposed the certain rules for identifying out of control process. There are 5 specific rules. So let me explain one by one all these rules. The rule 1 is very simple. A process is assumed to be out of control. Please note this point, that is, it is assumed to be out of control. Actually, it may not be out of control. Your, as you look at the process, the kinds of, the data patterns you observe, you find you are concluding at this point in time that the process may be out of control. You are not definite. It's clear. So this interpretation may be wrong. Okay, when we discussed the type 1 error and type 2 error, we mentioned this point. So please refer to these two concepts once again if you have any doubts. A process is assumed to be out of control if a single point plots outside the control limit. So here all these sample points are plotted. with these upper control limit and lower control limit, what you find that the fourth point is plotted outside the upper control limit. So immediately you conclude that at this point in time, is it okay, something has gone wrong and the process may go out of control or might have gone out of control. Okay. So this is the rule 1. Simple. Now what is rule 2? The rule 2 is a process is assumed to be out of control if 2 out of 3 consecutive points fall outside the 2 sigma warning limits on the same side of the central line. Is it okay? So that means what we have already mentioned in the previous lecture sessions, that what is a warning limit. Is it okay? So warning limit by conventions, they are placed at plus minus 2 sigma limits from the central line. Okay. Now so this is warning limit, this is also warning limit on the other side of the central line. Now this distance between the central line and the warning limit is plus 2 sigma on this side, and on the other side it is minus 2 sigma. Okay. Now what do you try to do? That means as I have already pointed out that the control chart is used as in prevention based quality control. That means as far as possible, you use the control chart in such a way that out of control condition is avoided. Is it okay? So that is your basic purpose. Now here, so that's why the warning limit. Now here what you find that this point and this point out of 3 consecutive points, they are plotted, okay, between the warning limit and the upper control limit. These 2 points are not out of control point, but make sure that means that you can improve this situation. That means it's all likelihood you are heading towards a situation where very soon you may cross this upper control limit boundary, and then the next point may come from an out of control state. So this is the time you should be very, very careful, right? And that's why this rule is prescribed, and so you may. So why out of 3 consecutive points, the 2 points already in this particular zone? Is it okay? Either the first or second, third may be anywhere, or the first and third like here, and the second may be anywhere, or the second and third, okay, consecutive 3 points, they are between they are plotted between the warning limit and the upper control limit, whereas the first point may be anywhere, it plots anywhere in this zone. Okay, so this is rule 2. What is rule 3? Rule 3 is we go one step further. A process is assumed to be out of control, okay, if 4 out of 5 consecutive points fall beyond the 1 sigma limit. That means you have a narrower band here. What we do, that means at a distance of 1 sigma from the central line, okay, on one side as well as on the other side, you draw these 2 parallel lines, and they are referred to as plus minus 1 sigma limit. Then you observe that the 4 out of 5 consecutive points, they fall beyond the 1 sigma limit. Is it okay? They fall beyond the 1 sigma limit. This is 1 sigma limit, right? So these are the 5 points we have: 1, 2, 3, 4, 5. 5 consecutive points. What you have noticed that out of 5 consecutive points, 1, 2, 3, and the 5th one, 3rd one and the 5th one, they are plotted outside of 1 sigma limit. So you may conclude that something has gone wrong. That means certain pattern you observe, and pattern means even if the points are within the control limits, but if you find there is a systematic behavior, systematic pattern, okay, you assume that the process is influenced by some assignable causes, and those assignable causes are present in the system, and that's why the process may be considered as out of control. Okay, so this is the basic idea behind concluding that the process has gone out of control or process is in control. So this is rule 3. Again, the fourth rule is the rule 4. A process is assumed to be out of control if 9 or more consecutive points fall to one side of the central line. So this is a very uncommon occurrence. That means there is a bias here. In this case, you will find that 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points out of say the 10 points that you have plotted, okay, in consecutive the time periods. What you have found that 9 out of 10 they are plotted on one side of the central line. Actually, when the process is in control, that means you plot the points, you get a pattern, and this the pattern must be a random pattern. Okay, that means there must not be is a non-systematic or random pattern. But this is not random at all. That means it is almost predictable. That means there are some assignable causes. Is it okay? So this rule is routinely followed. That is rule 4. In many cases, in many organizations, for many processes, they are tempted to use rule 4. The last rule, that is rule 5. A process is assumed to be out of control if there is a run of 6 or more consecutive points steadily increasing or decreasing. Now, what is a run? The run means actually a sequence of same type of observations. Actually, it's likely observations, a sequence of a group of observations. Okay, they are of similar nature, right? So this is basically a run, and whenever you say the run of sample points, that means the total the run length you also must specify. That means here is a run of 6 or more consecutive points. They are of similar nature. So here what you find that 1, 2, 3, 4, 5. Is it okay? So if a run of 6 or more consecutive points, that means here 1, 2, 3, 4, 5, 6, 7, 8, 9. That means 6 points. That means 1, 2 constantly increasing these values. Getting my point? Or the constantly decreasing. That means there is a trend, increasing trend or decreasing trend. In the set of plotted points over the time period. Is it okay? So obviously, you may conclude that there exists some assignable causes in the process, and the process behavior is influenced by those assignable causes. So immediately you may assume that the process has gone out of control. Now, here you might have noticed that whether it is rule 1 or rule 5 or rule 4 or all these rules, all the points they are existing excepting the rule 1. Okay, all other rules you will find that the plotted points they do exist within the control limits. Okay, but still they are referred to as out of control conditions. Why? Because there are two conditions. One is the necessary condition that you have to satisfy before you say that the process has gone out of control. The first one is, the necessary condition is for concluding that the process is in control state. That is, the no points are plotted beyond the upper control limit or the beyond lower control limit. This is the necessary condition. But then what is the sufficient condition? Sufficient condition is, even if all the points are plotted within the control limits, make sure that that there is a plot pattern you will observe, and when you look at the plot pattern, you do not find any systematic behavior. That means it must be a non-systematic behavior and as well as the random pattern. So sometimes if you find randomness in the plotted pattern, okay, they're all existing within the control limits, you say it's a natural pattern. So what we are asking for in a process which is considered to be in control, that are you getting a natural pattern? Is it okay? So later on we'll discuss about the different kinds of patterns. Okay, so we will study it in more depth. What are the other rules? Many companies, based on their experience and referring to their database, they have proposed many kinds of rules. So you should also be familiar with those rules. Is it okay? Detecting patterns on the control chart is an important objective of control charting. Point number 1. It is said in this context that construction of the control chart is very easy. You follow the steps, okay, you learn the steps, and you can control, you get the data, and you can propose a control chart of any type. But interpretation of a control chart is very difficult. That means, so while you interpret all these patterns, you must have a process knowledge, and unless you have the process knowledge with respect to a particular process, say a machinery or a facilities, is it okay? You must have a thorough knowledge about its behavior, its design, its performance, okay, you must be familiar with its past performance. Then only you may interpret these patterns, that what are the possible causes, okay. You may observe various kinds of patterns on the control chart. We'll refer to this later on. Many researchers and authors of textbooks on quality have specified certain rules for raising suspicions on the behavior of the process. That means sometimes you are not sure whether the process is controlled or out of control, but you, by looking at the pattern, you may feel that something might have gone wrong. So these are referred to as the suspicions. So what are the suspicions? So you are again, many companies, many researchers, they say that why don't you follow these rules? So what are these rules? And these rules are very simple to understand. Whenever I'll just read them out. Whenever in 7 successive points on the control chart, on a control chart, okay, so there are different kinds of control chart. In a given situation, you just pick up one relevant control chart and you start using it. If you find in that control chart, all are on the 7 side of the central line, so something has gone wrong. It's a systematic behavior. Next rule is whenever in 11 successive points on the control chart, at least 10 are on the one side, same side of the central line. Is it okay? Whenever in 14 successive points on the control charts, means through their empirical study, okay, these companies, these organizations, or these researchers, they are proposing these rules, very simple rule. So out of 14 successive points plotted, if you find at least 12 are plotted on the same side of the central line, and you extend it, whenever in 17 successive points on the control chart, at least 14 are on the same side of the central line. And the last one, whenever in 20 successive points on the control chart, is it okay? That means here is a situation whereas getting 20 sample points is not that difficult. Is it okay? Maybe while you collect the data, you may collect the data through an automated system. It's not necessarily that it is a manual system. So out of 20 successive points on the control chart, at least 16 are on the same side of the central line. Many such rules are proposed by several organizations based on their experience in dealing with the process. Now, I'll just briefly I'll tell you, or I will discuss the next topic. That is, I will make some introductory remarks related to the control charts of one type, that is referred to as attributes type. Is it okay? There are 2 kinds of control charts, the broad classification. One set of control charts are exclusively are used when you deal with the attributes data, and the other set of the control charts with the general purpose as well as the special purpose you use when you deal with the variables data. So before I elaborate on this, let me define what is an attribute. So what is an attribute? Any student in this particular course always he or she will be dealing with several kinds of data. So the first thing he or she needs to do or needs to understand what type of the data he or she is collecting. So this is the broad classification. So he or she may collect an attribute data. So an attribute is a quality characteristic, okay, related to a component or a system, or say the product as a whole or a service, is a quality characteristics for which a numerical value is not specified. So it is measured on a nominal scale. I have already referred to the nominal scale. There are 4 types of scales already. So it falls in the category of the nominal scale. And what are the examples? The taste of a certain dish. Can it be measured? It cannot be measured. Is it okay? So either it could be very good or very bad like this, or it could be fair like this one. So is level acceptable or unacceptable? Like say, the kinds of the painting you have done on the surface. Is it okay? On a metal sheet. So by looking at the surface, so the painted surface, you say yes whether it is acceptable or not acceptable. So these are basically attributes data, and you might say it is exceptional, good, fair, or pure. So as I've already mentioned, this is in nominal scale. Now you need to use control charts for attributes at an aggregate level of an organization. There are different levels. You have the strategic level, the top management level in organizations in a hierarchy. You have next is the middle management level, and then the third level you have the operations level. And then the operations levels you could have several the departments. Under each department there could be several sections. Under each sections there could be the different the work zones or work areas, and in each work area there are processes. So the process is what we say all the time, the process control and all. So the question is that where do a particular process where do they exist? Obviously at the shop floor level, at the operation level. So now this control chart for the attributes, they're essentially used at a particular level. That means not at the shop floor level, not at the operations level. That means at the process level. They are used at the department level, or they are used at the the function level, or the or the organization level. So okay. So there's a point to be highlighted, and there are 5 types of control charts in these categories. I will name them, but before I name them, you also must know what is the main purpose of using such a control chart. So the main purpose is to identify the location, like an area, work area, or a section, where the generation of defects or defectives needs to be controlled with priority. This is very, there are 2 issues involved. One is, the location of the cause. That is very, very important, because ultimately when you deal with a control charting, you are dealing with the causes of variation. So you first must know that here is a cause, where does it locate? So you have to locate it, the location of the cause. So for that, it's very important to use this sort of control chart, attributes control charts. And once the location is known, then you search for the the exact the causes and what are the types of causes. Is it okay? And then you search for ways and means to remove them. Is it okay? So for that you need to use a different kinds of control chart, that is referred to as a control chart for the variable. Different types of control charts are grouped into 3 categories. That means there are 5 types. They are classified under 3 categories. First category includes control charts that focus on non-conforming. Is it okay? That means it is basically a defective product. As I already defined what is defective, and the defective is a general term. Is it okay? Any user of the product may use, but as a technical person, okay, as an engineer, you say that it is non-conforming. So there are 2 charts we use. One is the proportion of non-conforming items. It refers to the proportion of non-conforming items. So it is referred to as the P chart. P stands for proportion non-conforming, where the sample size N may be a constant or may be a variable. So both the cases you need to consider. One extension of proportion non-conforming is sometimes at the operation levels. You may face the difficulties in calculating this proportion non-conforming. So you say that why don't we use the number of non-conforming items? Is it okay? You don't need to calculate the proportion non-conforming. Of course, in this case, we assume that the sample size is constant across the samples. So this is referred to as NP chart. The second category deals with three charts that focus on the non-conformity or the defect. Okay, on a single piece there could be many types of defects. So for each defect you select a defect which may be considered to be significant, a very critical one, and for which you need to construct a control chart. So the chart for the total number of non-conformities, assuming that the sample size is constant, that is the C chart. The chart for non-conformities per unit, that means when the sample size varies across the samples, we need to construct the U chart, and obviously it's a variable sample size case, and this is applicable to situations in which the size of the sample unit varies from sample to sample. Is it okay? That is the elaboration. And in the third category, the chart for demerits per unit, we have the fifth one, that is referred to as the capital U chart, deals with combining non-conformities on a weighted basis. That means there could be different types of defects or non-conformities on the same item, on the same product. What you need to do, that means depending on its impact, like say the defects could be very serious defects or non-serious defects, major defects, minor defects. Now accordingly what you do, each type of defects you need to consider, and each type of defect is to be weighted. Is it okay? So you need to combine these non-conformities on a weighted basis such that the weights are influenced by the severity of each conformity. So this is referred to as the demerits. It's a per unit basis. That means sample size remains constant. Okay, so or it could be a variable. So this the five. Now proportion non-conforming chart will be proportion P chart or the C chart or say the U chart or say capital U chart. We'll be discussing with examples. Okay, but there are the many issues involved, so I'll be discussing in the next interaction with you. Okay. So this is the reference. Always you can refer to this textbook. Okay, and so the basics we have discussed, and then we'll take up all these control charts one after another.